So, let us continue our discussion with the density operator treatment of NMR experiments. We have described previously the formal definitions of the density operator, the time evolution of the density operator, and we have shown what kind of an equation governs the time evolution of the density operator. We have also seen what kind of a solutions exist in the presence of the RF and in the absence of the RF. So, a generalized NMR experiment which will consist of several pulses with interleaving evolutions under the influence of different Hamiltonians, and this is as indicated here in this chart. This is a repetition from the previous one for continuity. So, you start an experiment here with density operator represented as rho 0, and then you apply a pulse P1. It may be any kind of a pulse, it may be a 90 degree pulse, 180 pulse, 45 degree pulse, or whatever, that is up to one's choice. Then this is followed by an evolution period, free precession period, which is under the influence of the Hamiltonian H1, and this happens for the time tau 1. Then this is followed by another pulse, we call it as P2, and once again it is followed by evolution under the influence of a different Hamiltonian H2, and that happens for a time tau 2, and likewise you continue for the P3 pulse, and then you have the evolution H3 tau 3, P4 pulse, and so on and so forth, till you complete all your pulses and you collect the data sometime here, and that is where the information is analyzed subsequently. So, you start from some particular time point here, which call it as 0, and you collect the data here with various kinds of manipulations happening in the various time periods here. The data you collect will carry all the information about that has happened in these previous times, and therefore we have to calculate this. So, we must know how to calculate the evolution of the spin system under the influence of all of this, and we have already shown that such a generalized pulse sequence can be represented by a time evolution of the density operator in this manner. You start with rho of 0 and you apply a pulse P1, the transformation happens as P1 rho 0 P1 minus 1, and this density operator now becomes the time t is equal to 0 for this portion of the evolution, and then it continues here, then that is represented by the e to the minus I by h cross h1 tau 1 and e to the I by h cross h1 tau 1. Now this whole thing becomes the time t is equal to 0 so far as the pulse P2 is concerned, and this is how it continues. So you see here, as you are progressing in the calculation, we go from the laboratory frame here to the interaction representation here, normal representation, the interaction representation, back to the laboratory representation, again interaction representation here, back to the normal representation, and so on. So you keep switching between the two representations for the calculation purposes, and these two representations are generally separated out in this way. You see, this whole calculation consists of these two kinds of evolutions. One is the e to the minus I by h cross ht rho e to the I by h cross ht. This is free evolution, this will apply to this period, this period, this period, and so on. And for the pulses we have this sort of a transformation p rho p minus 1, and this will apply to this one, this one, this one, this one, and so on. Okay. So this is quite a involved calculation, as we saw earlier, because each one of these operators will have to be represented as a matrix, and the matrices become larger and larger as we go to larger and larger spin systems, and different kinds of flip angles of the pulses, different phases of the pulses, all of that will complicate the matters quite substantially. So therefore a simplification was developed, and that is called as the product operator formalism. To simplify the above calculation, the product operator formalism has been developed for weakly coupled spin systems. Notice here the key elements, key points here I would like to underline here. One is this weakly coupled spin systems, you have to highlight this point. This is applicable to weakly coupled spin systems. The density operator is expressed as a linear combination of some basis operators which are represented as Bs, and these constitute a complete set. So, these are important terms here which one has to understand. You have already studied these situations earlier, but let me try and recap these to some extent. What is a weakly coupled spin system? So, weakly coupled spin system, this was an important things to remember. So, if you have two spins, both are spin half, okay, and if we have a coupling constant between them J and the chemical shift separation between them is delta, then if it is much less than 1, then we say it is a weakly coupled spin system. And this has been studied earlier when we actually went through the analysis of NMR spectra, how the spectra get complicated when this condition is not satisfied. By and large, in the modern spectrometers, when you have very high magnetic fields, this condition is usually satisfied for most systems, and therefore it is convenient to work with the theories which are developed for weakly coupled spin systems. And what is the consequence of this? So, if you look at the spin systems and want to calculate the various eigenstates and the energy levels of this, it turns out that the product functions are the eigenfunctions. If I have, for example, one spin, the states are alpha and beta. This is one spin. For two spins, each one of them is alpha beta. Then we said we have the product functions alpha alpha, alpha beta, beta alpha and beta beta. These are the eigenfunctions of the spin system. For three spin systems, then we will have product of three functions. We have alpha alpha alpha, alpha alpha, alpha beta alpha, beta alpha alpha, beta beta alpha, and then alpha alpha beta, alpha beta beta, beta alpha beta, beta beta beta. So, we have 8 eigenfunctions here. So, the reason why I am saying is the product functions are the basis set. So, here all these functions represent the complete spin system. Any situation can be expressed as a linear combination of these wave functions. So, that takes me to the next point there. Just as you are able to write a basis set and able to describe the complete wave function for a given spin system as a linear combination of these various functions, if I call this as UNs, each one of them is called as UN, then we wrote psi is equal to summation Cn Un, we wrote like that earlier. So, these UNs are these various basis functions, and one can write a generalized wave function as the linear combination of these basis functions. The same principle will be used for the product operator formalism, where we will represent the density operator as a linear combination of some basis operators. So, therefore we write rho of t as summation BST, this capital BS. These constitute what are called as the basis operators, and these are the coefficients which will contribute to the summation here, and that whatever are the ones which are contributing here, that will determine the nature of the density operator at any point in time. So, what are these basis operators? And these must form a complete set, just as we talked about the eigenfunctions, the forming a complete basis set so far as the wave function is concerned. Here these operators must form a complete basis set, so that we can represent any density operator as a linear combination of this. Now, having said that, now let us try and calculate what is the transformation that happens for these density operators. For the rho dash, now we introduce the rho of t here, the rho of t was here, right. So therefore now it becomes summation Bs e to the power minus I by h cross Ht Bs e to the I by h cross Ht. And similarly for the pulses we have the rho double dash, which is summation Bs P Bs P minus 1. Okay. Now how do we choose these basis operators? There are many ways of choosing these basis operators, and we will take only one of those examples, which is the one which is most commonly used for various calculations. For certain situations some other kinds of basis operator sets are also used, but we will use the one particular one which is most commonly used. In every case however, these are formed from what we know already as angular momentum operators. These are formed from angular momentum operators. Which is a very natural choice to make, because your Hamiltonians consist of the angular momentum operators. Therefore, there will be kind of operationally easier things to do when you have the basis operators also expressed in terms of angular momentum operators, which do satisfy the condition of completeness, and therefore the calculations also become relatively easy. Now what are the angular momentum operators? Typically we have in the Cartesian space, this is the unit matrix, and we have the 3 angular momentum operators Ix, Iy and Iz. So we build on this, we build using this. So for a single spin if it is, then I will have one Ix, Iy and Iz, and E is a unit operator, and this is the normalization factor half, which is there in every case. Now if I have n spins, so we said for one spin we had 4 operators, right. One was the unit matrix, and then you have Ix, Iy and Iz. So if I have n spins, I will have how many combinations I can make from each one of those. Each one of them has 4 possibilities, and therefore I can create 4 to the power n combinations of these various kinds of products I can take, because I should not be missing any portion of the density operator. So all the spins must be represented, all situations of all the spins must be represented, therefore all the operators of the individual spins must find a representation in your basis set. Therefore if I have n spins in a coupled network, there will be total of 4 to the power n elements in the basis operator sets. So for example, for 2 spins there will be total of 16 operators. So for Cartesian space, these are, we have this E dash, this is basically related to the unit matrix. We have this 1/2, that one we will explicitly see what those ones are. Then you have the x, y, z of one spin, and then the x, y, z of the second spin. Then I take individual products of each one of these with the other spin, and this is again a normalization factor here too. I will have 1x, 2x, 1x, 2y, 1x, 2z, and next 1y, 2x, 1y, 2y, 1y, 2z, and 1z, 2x, 1z, 2y, 1z, 2z, and these are the normalization factors in each of these cases. So likewise, if you go for 3 spins, how many operators you will have? Notice in the previous case we had a total of 16, 4 to the power 2. Okay. Now here how many we should have? If you have 3 spins, I should have 4 to the power 3, so that means 64 operators. So here it is the unit matrix once more, and then I will have here IAP, IMP, IQP, where P goes from X, Y, Z. So there will be total of 9 operators. A, M and Q are the 3 spin symbols, okay, and P it goes from X, Y, Z. This represents the Cartesian index, okay. So and then I will have 2 spin products. So 2 IAP IMR, 2 IMP IQR, and then 2 IAP IQR, and here notice I am varying A, M, P and R both. So there are AM 3 spins A, M, Q, right. So I will have product A to M, M to Q, A to Q. These 3 products will be there, and for each case I will have the P and R varying as X, Y, Z. So there will be total how many? Total of 27 operators. So this is, there are 3 here, P takes 3 values, R takes 3 values. So therefore 3 into 3 into 3, so you will have a total of 27 operators. And then you will have the 3 spin products. The 3 spin, because all the 3 spins combinations can be present. So you have 3 spin products. So here again you will have a normalization factor 4. Now I have the products of all the 3 spin operators here corresponding to each of the 3 spins. So A, M, Q, and then I will have here indices P, R, S. All the 3 PRS can go from X, Y, Z. So therefore this is 3 to the power 3, and I will have again 27 operators here. So total of 64 operators I get for the 3 spin system. So likewise I will get many more as I go to larger and larger spin systems. However, by and large we generally do not come across operators which are more than 3 or 4. Now let us see what do these operators encode. Okay, we created the various basis operators and we said they represent the density operator, and we have seen the density operator contains various kinds of populations, single quantum coherences, double quantum coherences, zero quantums, multiple quantum, various kinds of coherences are present. Now what do these base operators represent? Which base operators, this is basis operators, okay, which basis operator represents what sort of information, what kind of information does it contain? So now for one spin, the Cartesian representations in the term of matrices are as you have seen here. Ix is, with this we have already calculated previously, is half 0 1 1 0. So there are 2 states alpha beta, and so therefore this is an off diagonal element in the, if you want to take this matrix, and if you put this in the density operator, this off diagonal element will imply a single quantum coherence, and that means it is X magnetization of a particular spin. This is the one spin, so therefore in the case of one spin it is the X magnetization of that spin. Now Iy is half 0 minus y I 0. This is once again a single quantum coherence because this is off diagonal element here, states alpha beta, alpha and beta. So this is a transition from alpha to beta, therefore single quantum coherence here, but this is a Y magnetization because you have, see, you have imaginary quantity here. The Iz here is the diagonal elements are non-zero, off diagonal elements are 0. Therefore this represents the populations, and the populations will indicate to you the Z magnetization. Okay. Now when we go to 2 spins, we calculate the matrix representations of the 2 spin operators in the following manner. We follow the same trick as we did for the pulses. You notice here I have here the unit operator as E dash, and E dash is calculated simply as this is the unit matrix here and this is again a unit matrix. You take a direct product because for 2 spins K and L it will be a 4 by 4 matrix. And what does this represent? So I take a direct product here 1 0 0 1 into 1 to 0 0 1. So I will get here, is not written here, but this will be only diagonal elements will be present. We can write that explicitly. We can write here, this will be 1 1 1 1 and all others will be 0. Right, 1 0 0 1, this will be 0, this will be 0, 1 0 0 1, and that is the direct product. If you take Kx, now in a 2 spin system I am trying to represent the X magnetization of the K spin alone. So therefore my operator for K spin is 0 1 1 0 X magnetization, then I take a direct product with a unit matrix here. So that is how I get a 4 by 4 matrix. So if I take this direct product here, 0 into this matrix give me this 0 matrix here, and 1 into this matrix give me the same matrix 1 0 0 1, and similarly here this 0 into this 1 into this matrix give me 1 0 0 1, and 0 into this gives me 0 0 0 0. So therefore, now what do I get here? Now this is the, if this were the density operator, you see what this represents. This represents the 1,3 coherence. I will show you the explicitly in the energy level diagram in the next slide. This is the 1,3 coherence, this is the 2,4 coherence, and these are the other corresponding elements on the other side. Okay. So therefore this represents X magnetization, take it as the K spin, and these are in phase single quantum coherences. In phase because these two coherences have the same sign. If I do ILX, now this is another spin. So how do I get this? To get this, I will have to simply reverse this order. Unit matrix I put it here and the X operator I put it here. So therefore unit matrix come 1 0 0 1 and 0 1 1 0. If I now take the direct product of this, you see I get these elements which are non-zero. In this case you had these elements non-zero, here I will get these elements non-zero and all other elements will be 0. So this will be now 1 2, 2 1, 1 2 and 3 4. Again 2 coherences which obviously belong to the different spin, and that we will see in the next slide here. So if I take Kx, I put the same matrix here and you see this is the 1,3 coherence and these are the energy levels of the two spins. 1 2 3 4, this is 1,3 transition, right. So 1,3 transition is this, 1,3 coherence is this, and here it is a K spin which is flipping. Alpha L spin is the same, alpha L, and it is a K spin which is going from alpha to the beta, and similarly here in the 2,4 transition it is a K spin which is going from alpha to the beta, L spin remains the same. Therefore these two are positive, these therefore this represent K spin coherences, and therefore that represent a K spin magnetization, X spin. Now if I were to draw this in terms of the coherence as the NMR spectrum, because the coherence will appear as magnetization which is observable in the NMR spectrum. So therefore these two transitions will be represented as 1 3 2 4 and both have the same sign because these coherences have the same sign. Now if I take the other one ILX, these elements are non-zero. Now what are these? This is 1 2, 1 2 is this and 3 4 is this. Okay. Now here it is the L spin which is flipping, the K spin is constant. That is why these are the L spin coherences. Okay. So once again therefore this implies X magnetization of the L spin which is in phase single quantum coherence. What it means in phase? They have the same sign. Therefore we call them as in phase, and these two transitions are in the NMR spectrum will appear in this manner 1 2 and 3 4. Now IKY, I do the same thing. I have this KY operator here and the unit matrix here, and therefore I get here the Y magnet the same elements except that I get here minus I, and similarly for L I get here minus I here and minus I here. So this represents the L spin magnetization, this represents K magnetization. But what about this I? I means it is imaginary. So this is 90 degrees out of phase, and that we call as the dispersive line shape. This will represent a dispersive line shape, because if I were to measure the X magnetization as in phase, then the Y magnetization will be the 90 degree out of phase. The 90 degree out of phase is the dispersive line shape. So and how does that look? So here we have here the IKY, these are the two transitions here, the same here 1 3 2 4, but in the NMR spectrum we will look at the 90 degrees phase shift, this will be a dispersive line shape, but these are in phase. In phase meaning this goes up and down here and this also goes up and down in this manner. So therefore these two transitions are in phase. These are dispersive in phase transitions. Similarly for LY we have 1 2 and 3 4, and these are once again in phase transitions, and 1 2 3 4, and that is because I have the same sign for this and this, right. Okay. So for this is clear about the two spin system, how the individual elements of the base operators are to be interpreted. What is the information content in the different elements of the base operators? What do they represent? Now extend it to 3 spin. The 3 spin I will make a beginning here, of course we will continue later with more details. Continue take a 3 spin system which is KLM, these are 3 spins. So now I said there earlier that there will be total of 64 operators. We will illustrate only some of those. Here we take IKX, ILX, IMX, which are supposed to represent the X mechanization of K, L and M. Now each one of them will have how many transitions? Suppose there is a coupling between K and L and M and K and M, all the 3 spins are coupled. Then I will have 4 transitions for each one of those, because each one of them leads to a splitting into 2, therefore I will have 4 transitions. Now the energy level diagram for the 3 spin system, there will be 8 energy levels as I mentioned to you earlier with the case of 2 spins. Here I will have alpha K, alpha L, ILM, alpha M. See, essentially one 2 spin system, another 2 spin system, except now you add the 3rd spin as alpha here and the beta here. So you generate a 8 level energy level diagram. So now each one of them, now the duplication happens, this states belong to one, these transitions belong to one spin, all the red ones belong to one spin and these green ones belong to one spin as before. And now you have the 3rd spin transitions happening from here to here, here to here, here to here and here to here. And all of those are represented in this manner. Since all of them are in phase, I must write them as absorptive line shapes here for each one of those. The individual transitions are indicated here for the L magnetization, the K magnetization and the M magnetization. So therefore this is the simplest. Here we are seeing the individual transitions of the K and L spins, and this we call them as in phase magnetizations because they are in phase with respect to the orientation of the other 2 spins. So regardless of what the other 2 spins are, other 2 spin states are, I have the same positive absorption signal, therefore we call them as in phase. The other things we will see in the next class. We stop here.